this video, this is going to be talking about acid-base reactions. We're going to be going over a lot of acid-base reactions, but that's mostly later on in the course. This is just a kind of a preview just to see where they are. This is the second type of reaction that I want y'all to know. Let's just go through some definitions. I have talked about the Arrhenius definition before, where an acid is something that ionizes to make H plus, or base ionizes to make OH minus. Easy way to see it is if it starts with H, it's an acid, and if it ends in OH, it's a base. That's usually a good rule of thumb to follow. Another definition to be familiar with is the Bronsted-Lowry definition. I taught you in first year chemistry that an acid gives and a base takes. So an acid gives a proton and a base takes a proton. By a proton, I mean a hydrogen atom. Okay, and so sometimes it won't always start with H, and so it will that covers a much broader definition. There's another definition called the Lewis acid and base, but those have to do with electron transfer, and that's actually organic level chemistry. Okay, that's even higher than this course. So and it's not tested on the AP test, so we'll just move on. We are familiar with the strong acid and the strong base. So when a strong acid and a strong base mix together, you can see right here that the net ionic equation is going to be this. Everything else will be a spectator ion. So all you're breaking down is just the acid, H plus, and the OH minus, and then you're getting water. If you have something strong, like a strong acid, and then you have something weak, like a weak base, and you put those two together, it will actually move to completion. Just like this down here. It's very, so we'll actually get something on the side. We'll get an ion kind of left over though. So this would be my acid. This is acetic acid or vinegar added to a base. This would be my strong base because it's an ion. Acetic acid is a weak acid. And then it would react to form water, and then you would have the acetate ion left over. There's more to this than that, but for now, for this chapter, this is good to go. So when you take an acid and a base and you allow them to come in contact with each other, they will neutralize each other. They will make a salt and a water. When just the right amount, just the exact number of molecules or the exact number of moles come in contact with each other, the acid is the substance is said to be neutralized. Again, anytime you see like it's written where it says base here, you could actually substitute acid as long as you substitute base down here where it says acid. You could flip those either way. You could neutralize either one. A titration is where we take advantage of the neutralization reaction and we can actually analyze a solution. You'll be able to take an unknown amount of an acid and then add base to it just to the point where you get it to a neutral solution. Then I know how much base that I added to the system, and so now I know how much acid is in my original sample. It's a pretty neat trick, and that's called volumetric analysis. The way that we'll actually do titrations in the lab is I'll show you 3 different methods, because we're going to do titrations enough that I can show you 3 different ways. This would be the first way, and this is the way we're going to start out with, where we have our sample and we'll add some kind of indicator to it. The indicator won't change the pH, but it will now change color as soon as it becomes neutral. So now I know when the sample is neutral. So let's just say that there's an acid in here, and then we'll say that we have our base in our burette. This burette is very accurate and very precise, and we can know the exact number, the exact volume that we add to the solution as the liquid level will go down. And then whenever I get to that color change, I will stop and I will compare how far the burette moved. Say it moved from here to here, I will now know how much volume I added. I can then use stoichiometry to find how many moles of my uh, base that I added, and then I can then find out, since that's the same number of moles that was in my acid, I now know how many moles and I know how much acid is in my original sample. It's a neat trick. I'll point out that we can use this for acids and bases, but we can also use this for other types of reactions like redox reactions. It's pretty nice, and we'll do that as well. To do a titration, we're going to need four different definitions. The titrant is the known solution that's usually in the burette. That's going to be something that we know the exact concentration, but we also know the identity. The equivalence point is very simply the moles of acid, where equals the moles of acid equals the moles of base. The exact number of molecules where they equal each other. That's going to be the most useful point. Graphically, we can show the equivalence point when we graph the pH versus the titrant added, or the volume of the titrant added. As we gradually add the volume of the titrant, the pH will steadily increase. Then we'll get to a point where it will dramatically increase to the point where it will jump very high, and then it will now the rate will now decrease, but it will still increase. But the pH will still increase steadily and reach a plateau or an asymptote. This would be the point where the slope would be undefined because the slope would be vertical. Again, we'll be covering this in much more detail later. I want y'all to just get a rudimentary understanding for what a titration is. The indicator is every chemistry student's favorite thing because it always changes color, and we're looking for the color change, and it's a lot of fun to try to see those. That's going to be what, and it will not change the pH whenever we add it. There are many different types of indicators. You want to choose one that is close, that will change colors close to the equivalence point. And I'll choose them for you usually. And the endpoint is going to be the point at which the indicator changes color. So the endpoint is what you see. That's based off of your observation. The equivalence point, the one before, is going to be where the molecules are exactly the same. So it's important to know the difference between the endpoint and the equivalence point. So now, based off of what I've shown you, would you be able to identify the titrant and the analyte, that's the substance we're looking for, in this mathematical example? Does this help you? What I'm going to start off is this is my titrant. This is my known concentration and my known volume. All I know is the volume of the analyte that I had, and that's my sodium hydroxide. So I will take my volume of my titrant and put it in the top left box. Then I will use the molarity to help me along the way. This is a great way to go. Notice that I put these in. I put my original volume in liters because molarity has to be in liters, and I applied my molarity so that I would cancel out the liters. Now I've got moles left over. That's my only unit I have to work with, and now I will see that since the solution was neutralized, it was at its equivalence point. That means that 1 mole of acid equals 1 mole of base. So now I can just use the calculator to find out my moles of base, and then divide by my volume to find my final molarity. It's a neat trick.